Today in this session we are going to learn about digital electronics, where we will concentrate on logic gates. So, digital electronics, and in this digital electronics we will talk about logic gates. So, logic gates are electrical devices which do some logical operation. Logical operation means, suppose I say input I give 1, output you get 0. 1 and 0 means, suppose 1 here is high output, high voltage, the output will be 0. Suppose we have a switch, so on off. So, some mathematical operations we call logical operation that is performed by these logic gates. So, before we talk about logic gates, let us see in digital electronics we talk about digital signals. So, the signals can be analog and digital. In digital electronics we will talk about digital signal. So, let us see first what is analog signal. So, analog signal. In an analog signal, so a signal that is voltage or current, a signal that is voltage or current which varies continuously with time is called analog signal, So, it can be a current or voltage. So, you see, if something varies with time, suppose this is voltage, it varies with time like this. So, this is an analog signal. It can have any waveform, suppose it is current and it varies like this. So, this is also an analog signal. So, this is an analog signal. Now, digital signal. So, in a digital signal, there are only two values, two discrete values, either high or low. In binary language, we say either 1 or 0. So, digital means, suppose here there is voltage. So, here suppose I say it is 5 volts plus 5 volts. So, you see up to this time this is 5 volt, then 0, then again 5. So, you see this either it is 5 or 0 or 5 or 0. So, no other values are there. So, this is what we say a digital signal. So, a digital signal will have only two entries, two discrete values, either some 5 volt or 10 volt, anything we can select, or no voltage. So, any two values are selected, whereas in an analog signal the voltage or the current varies continuously with time. Now, let us see digital circuit. A digital circuit can handle only two discrete values, i.e. digital signal. That means a circuit which handles digital signal is called a digital circuit. Now, in digital circuit we have to see what are logic gates. So, the electrical devices, anything, it can be electrical or electronic, the devices which takes one or more input and gives only one output, that is unique output, unique is called a logic gates, a logic gate. Now it does logical operation. A logic gate does some logical operation. This is what we have to learn in this topic. Now any logical operation is expressed in some tabular form that is called truth table. Truth table. It is a usual practice to show the input signal and the output signal in a binary language. Binary language usually in the form of a tabular form called truth table. So we describe the input and output of the logic gate in a binary language. Binary language means mathematical language with using two digits 0 and 1. So generally when the signal, you see what is 0 1, suppose this is T and voltage, and sometimes the voltage is high, then 0, then high. So that means for this time the signal is 1, then 0 and then 1. So whenever we have a high value of the voltage, I will say it's 1, and then when it is 0, then I say 0, that means no voltage means 0, low value is 0, high voltage, so 1. So any logical operation can be described in a binary language as a combination of 0 and 1. So now let us see different logic gates. So there are some basic logic gates called OR, and NOT logic gates. So first let us see OR logic gate. So now you see there are different types of logic gates. So they are basic type, and this is universal type. So basic types is again OR gate, another one AND gate, next one NOT gate. Now these are basic building blocks. Now when I mix up these two, then I will get another, that is NAND gate, and then NOR gate. Now they are called universal because if I have only NAND gate, I can develop all these gates. If I have a NOR gate, I can develop all these gates. But simply if I have a OR gate, I cannot develop AND, NOT, NAND and NOR only by getting an OR gate. So these are basic ones and these are universal gates. So first we will see OR gate, then AND, then NOT, then these we will see. So let us start with first with OR gate. Now let us see OR gate. So this is called any or all gate. So in an OR gate there is two or more than two inputs, but only one output. So how many input can be there? At least two or more than two. So input can be more than two, but output is only one. The output is high if any of the input is high. Any of this input is high. So we use a special type of mathematical algebra called Boolean algebra to describe this operation. So in Boolean algebra, this operation is described as y is equal to a plus b. So this plus is not just addition, it is an OR operation. So this is how we define the logical operation of A, where A and B are input. Here keep in mind y is output and A and B are input. Now let us see truth table of OR gate. So let us see how we write the truth table. So you see here, we will first write A, so A, then B and then Y. So here first, suppose A is 1 and this is 1. So you see this is any or all gate. So here 1 and 1, so Y is 1. Next this is 1 and this is 0. So any of the input is high. So you see here 1 is high, so output is high. Now this is 0 and this is suppose 0. So this is 0, 0, both are 0, so here output will be 0. None of this is high. Here 0 and 1, so this side B is 1 high, so it will be high. So this is the truth table for an OR gate. The symbol, this is what we said, that the logical operation is described in the form of tables. So this is what truth table is. The symbol for OR gate is this is A input, this is another A input and this is our output Y. So this is the symbol of an OR gate. How we do the logical operation, not in binary but this voltage form. Now suppose the input, this is input of A, that is in current form or voltage form. So you see here, let us see here time is there and this is the voltage. This input A is here and we have given another input T here. So this is for B and this is for A. So here this is suppose plus 5 volts up to here, then it is 0 up to here, then like this. So this is how, this is the, I am shading to tell that this is the graph is up for this line and here. So this is the voltage waveform for A, and for B it is suppose again 5 volts plus 5 volt up to here, then here and then here. So this voltage waveform for this is like this. So this is how voltage, this is the digital signal in A, this is the digital signal in B. That means if we have a OR gate where we want, this is A and this is AB. So the digital signal given is something like this. This signal is given here and this signal is given here, something like this. So A and B are given these signals. How we will get Y if this is an OR gate, that we have to do it. So now you see here, this is time axis and C. So we will see for these instants of time. So here A is 1 and here this is 0. So this is 1 means 5 volt and here this is corresponds to 1 and this is 0. So up to here A gives 1, this gives 0. So 1 and 0 gives 1. That means here I will get, this is Y output, here I will get 5. So I am shading this like this. So 5 up to here. Next, from between these to this gives 1 and this gives 1. So this 1 and 1. So 1 and 1 will also give, you see 1. So again we will get the same type of signal. This is again 1. Next, this is 0 and this is 1. So again I will get 1. So output will be this. Then this is 0, this is 1. Again I will get it to be 1. Next, this is 0 and this is 1. So again I will, so for all these A plus B, these entries will be like this. So this is how currents we will get, every time we will get 1. If I will draw the truth table of this, the truth table of this will be something like this. So for this operation, the truth table will be, now you see, for this 1 0, so 1 0 is the input, here 1 1, here 1 1 is the input for this part. For this part 1 0 1 is the input, then 1 0 1 0 is the input, next here 0 1 is the input. So these are the different inputs for different time intervals. They are, we have assumed that they are equal time intervals. So 1 0 will give 1, 1 1 will give 1, 1 0 will give 1, 0 1 will give 1, 1 0 will give 1. So if any of the inputs or all of the inputs are high, we are going to get high output. So now let us see the operation of a OR gate. So this is inside the OR gate, this is the symbol of an OR gate. So you see this is Y here and this is A and B. So inside the circuit we have this arrangement. So let us see how the device manages to produce such an output. So the truth table, now let us write the truth table for this. So the truth table for this is, this is A, this is B and this is Y. So we are going to write down to the truth table here. So first, here we have two diodes, crystal diodes, PN junctions. Here let us call it D1 and this is D2. This is connected to a load resistor and which is earthed. Now this is the output Y and you see this is earthed. So if you have to take the output, you can take across the load resistor between these 2 points. Now here A and B is the input is given at A and B. So this is a part of the circuit which is connected to a cell whose negative terminal is grounded, and this is suppose 5 volts. So this point denotes 1, 1 means on position, that is it, the moment this point is connected to A, that means A acquires that 5 volts. And if A is connected to this, that means earth, that means it acquires 0 volts. So let us see first, if I connect A and B both to 1, that means I have given 1 and 1. So if I give 1 and 1, that means at that time what will happen? You see at that time, that means let us see what will happen with these two signals. That means this becomes 5 volts and this becomes 5 volts. Now you see here, this is 0 volt, this point is at lower potential and this point is at higher potential. This point is lower, so current will flow in this direction and diodes D1 and D2 are conducting. So this for first one, so A is given 1 and B is given 1. 1 means 5 volts. Both the diodes D1 and D2 are conducting, forward biased and conducting. They are forward biased and they are going to conduct. So when they are going to conduct, you see this forward resistance is very less. So, you just see this circuit small forward resistance and here large load resistance, this is 0 volt and this is 5 volts. So, majority of the potential drop will take place here. Suppose this is 0.1, so this is 4.9 volts. That means majority, so it becomes 5 volts. That means at Y, this is the Y point, you will get a high signal. So, you will get 1. So, 1 will give 1. How? Because D1 and D2 becomes forward biased. You see, this is the case. This is a very important case. And you see this, either you can take this one or you can take this one. So, both potential drops will be 0.1, 0.5 something and here 0.4, 0.9 something like that. So, here forward resistance is very less compared to this. So, majority of the potential drop is taking place here and so you will get at Y high voltage that corresponds to 1 position in the binary notation. Now, second position, what we do, this was my 0 position. So, I connect this to this and this, that means this is 5 volts and this is 0 volts. That means my A is 1 and this is 0. So, let us see what happens. So, when you see this is 0 volts and this is 0 volt, it is not here, this, let us leave this, come to this point. This is 5 volt and this is 0 volt. So, it is conducting, but this is not conducting. Since it is not conducting, current won't flow here. So, current will be flowing through this diode D1. This is load resistor and this is 0. So, this current flows. So, A is equal to 1 and B is equal to 0. Now, here only D1 is conducting because it is forward biased and D2 is not conducting. So, the current actually flows in this circuit. So, there is a potential drop, majority potential drop here. So, it is again at high voltage. Suppose this is 5 volts here, this is 0 volts here, majority potential drops here. So, it is again high. That means 1, because here again Y you will get equal to 5 volts. So, if any of this D1 is going to conduct, that means current if flowing in this way will give this at a high potential. Now, come to the third case, we will take this and this 0 and this 1. So, we expect this again to be 1, let us see how. So, A is equal to 0 and B is equal to 1. That means A is 0 means it is earthed, suppose this is 0 and B is 1 means 5 volts. So, earthing means I said it is 0 and so if I connect A with this, it becomes 0 volts. So, in this case this D2 is forward biased and this is 0 volts not current flowing here. So, when the current flows here, let us see B, this current D2, this is D2, the current flowing is like this. This is load resistor and this is 0 volts, this is 5 volts. So, current will begin to flow and so here you will get again Y is equal to 5 volts. Now, let us see what about this. You see, you have a 5 volts here and 0 volt here, 0 volt here and nearly 5 volts here. So, it gets reverse bias, no current. So, current flows only along this direction. So, current does not flow here. So, here diode D1 is non-conducting and D2 is conducting. So, current flows through the load resistor and so Y is equal to 1, that is high voltage. So, here we got 1. So, next the last case is 0 0. So, 0 0 means here I am going to give 0 volt to both this, that means I am going to connect this to both. So, 0 0 means both are reversed bias. So, this is the fourth option, A is equal to 0, B is equal to 0 I both diodes D1 and D2 are reverse biased and so non-conducting. If they are non-conducting, current does not flow, then this is 0 volt, this is 0 volt, so Y becomes 0. So thus Y is 0. No voltage means 0. So you see, this is how we write the truth table and what is happening in electrical terms in this logical operation. Let us see the operation of an AND gate. So AND gate is also called all or nothing, all or none gate. So it has two or more inputs just like the OR gate, but only one output. So this is similar to OR gate in inputs and outputs. So two or more inputs can be there, but only one output. The output is high, the output is high if all the inputs are high and the output is low if any of the input is low. This is the AND operation. The Boolean expression for AND operation, AND gate, is Y is A dot B. The symbol for AND gate is, this is the symbol and this is curved here. This is the input A, B if two input, if C another input, and here we have Y. So this is the symbol for AND gate. The truth table is like this. This is the truth table for this. We will write A here, we will write B here, and this is Y. Now this is 1, this is 0. So this will give 0. This is 0 and 1, this will give 0. This is 1 and 1, it will give 1. 0 and 0, it will give 0. This is what AND operation is. Now let us see in the wave form this operation, AND operation. So this is AND operation. So here we are going to give the signal A and this is time. This symbol is here, here voltage is plotted and suppose I say it is plus 5 volts and here A is there. So let us consider some intervals, this interval 1, this another one, second, they are equal intervals, third interval, fourth interval and fifth interval. So A is up to here and we have next B. B is plotted here, B, and then we have this is B here plotted, and next we are going to plot that Y that is A B, that is AND operation this time. So now let us see, here I get this, then 0, then I get again 0, then 0. That means this time I have got here up to t time this, then next here I got this. So, only in these intervals I have plus y for this, and for here I have plus 5 volts for here up to here, and then I have here only. So, now let us see how the voltage will be in y, that is what is the operation A and will give. Now, here you see, just see, this is 1 and this is 1. So, we will get this 1. So, AND operation tells that 1 1 will give 1. Then here I get 0 and 1. So, it will be getting 0. Then here I get 0 0, again here 0. So, here I get 1 0 0. Next this is 1, this is 0. So, I will get 0. So, you will get high if both the inputs are high. Here this is 0 and 1. So, we will get 0. So, I will get only high only when both the inputs are high. So, in this way the waveform you give A waveform like this, you give B waveform like this, you will get the digital waveform at y as this one only. This is what A and B is. So, now let us see how AND gate operation takes place. So, this is the truth table and this is the circuit. In this circuit, what is difference from OR gate is that we have reversed this D1 and D2. Previously it was P was this side, now P is this side, and now previously it was earth. Now we have connected this to a cell. Suppose this is 5 volt cell and then this terminal is earthed. So, this is the difference. Here there is a cell and these two are inverted. This is the difference between OR gate and AND gate. So, now let us see one by one all the cases. So, first case is if A is equal to 1 and B is equal to 1. A is equal to 1 means it is connected to 1 volt, that is it is 5 volt, and it is connected to 1, so it becomes 5 volts. Now, here you see across the load resistor, you see here 5 volt is there and this here 5 volt, here 5 volt this side and this side 5 volt. So, there is no potential applied on D1 D2. So, there is no current flowing in this wire. So, no current flows across the load resistor. So, if there is no load current, then there is no potential drop and full voltage of this will be applied to here. So, in this case I will get 5 volts, that means hence, so y is equal to 1. So, if this is 1 volt, this is 1 high, this is high, that is 5 volt means high, here also I got 5 volts, so high. Now, we will say 1 0 case. So, second combination of A, if A is equal to 1 and B is equal to 0. So, now A is 1 means 5 volt and B is here 0 means we connect it to 0. So, now you see what happens, this is 5 volts and so there is no potential difference across D1, but this is 0 volts. So, this becomes forward biased. D1 is not conducting, but D2 is conducting. So, D2 is conducting. So, when D2 is conducting, you see current flows along this, and so when the current flows across this, there is a potential drop here, and you just see this circuit, this D2 diode is there, this diode, this is load resistor and this is 5 volts and then it is connected to 0. So, 0 means you can say it is connected to earth. So, you see this 5 volt potential can drop takes place here and here. Since this forward biased resistance is very less, so majority potential drop here takes place. So, here this potential is 0. So, in this case it will be 0 volts. So here you will get 0 volts, that means off state, that becomes 0. So D2 is conducting here. Now case 3. So if A is equal to 0 and B is equal to 1. So here this is 0 and this is 1. Let us see what happens. So when A is 0 volt means this is 0 volt I have applied, and B is 1 means high, means 5 volts applied. Sorry, this A is 0. A is 0, previously I have taken A1, previously it was this was 5 volts and this was 0 volts. So D1 is not conducting, but D2 is conducting. So now this 0 and 1, so this A is 0 means this is A is 0 here. Now in this case A is 0 means this is 0 volt and B is 1 means 5 volts. So D2 is conducting. So here, okay, so here you see this is 5 volt and this is 5, this is not conducting and this is conducting. So in this case this D1 is conducting. So the current flows in this direction. So D1 is conducting and D2 is non-conducting. So thus the current flows across the load resistor. The current flows across the load resistor. So if current flows across the load resistor, then what will happen? Potential drop will take place and this will get 0. So again I will get 0. So Y is equal to 0. Fourth option, if A is equal to 0 and B is equal to 0. So if both are 0, you see if this is 0 and this is 0, so what happens now? This is 0 and this is 0, so both will be conducting. So current flows, so D1 and D2 are both conducting. So Y is equal to, when it conducts both, so current flows across this, and so potential drop here is 0. So Y is equal to 0. So 0, 0 gives 0. This is how the AND gate operates. So now come to NOT gate operation. It is an inverter. So in this gate we have only one input, and only one output. It is the simplest of all logic gates. The input is, the output, you see the output is high if the input is low. And the output is low if the input is high. So this is, it inverts the signal, we can say. So the Boolean expression for NOT gate is Y is A bar. Y is equal to A bar. The truth table here is very simple. This is Y and the input suppose is A. If I give 0, we get output 1. If I give 1, we will get an output 0. This is the simplest truth table. The symbol used for this is simple. This is the symbol for a NOT gate. NOT gate. This is the symbol for a NOT gate, where input is given this side, this is that side. This is the symbol of a NOT gate. Now let us see the same operation not in terms of this binary language, but in the language of currents. Here this is voltage and I have selected plus Y volts. This is the A input. We have again here we will plot Y, this is T, and we have certain temperature time ranges. So this is 5, next it is 0, and next it is 5, then it is again 0, then it is 5. Suppose this is the signal A given, this is the input A given, this is the digital signal. So this is 1 0 1 0 1. So in the output we will get 0, 0 will be inverted by 1, this is plus 5 volts, this is 1, so 0 0, so it will become 1, then 1, then it will become 0. So we will get the output like this. So you see 0 is inverted to 1 and 1 is inverted to 0. This is the waveform analysis of this NOT gate. So now this is a transistor circuit which is inside a NOT gate. If we have a NOT gate, inside this NOT gate we have a transistor circuit like this. This is the A and this is the output is taken like this. So this whole is embedded in this. This is emitter and this is the base and this is the collector. This collector is connected to a load resistor which is connected to a plus V volts. This is here R base which is connected to minus V, and this through B is base signal is given to the base with a resistance RH. So now when I earth it, when A is connected to earth, then the transistor comes into cutoff mode. These values are so selected when A is earth means 0 potential is applied, then here you see then this gets reverse bias and so it is in cutoff mode, and the transistor and the collector current is 0 and the collector current is 0. So when there is no collector current flowing here, then as a result the full V voltage comes at Y. So Y is at the V voltage. Suppose V is here plus 5, then it gets 5 volts. However, now when A is sufficiently large potential, say V potential, then the transistor gets into saturation mode. So when we apply V volt here, then it gets saturation, and so the transistor conducts. So when the transistor conducts, potential drop here takes place, and so here Y is 0. So you see we can denote this A and Y. So when you apply 0 volt here, it conducts, and so it does not conduct, and so it is at high, and when it is 1, that means 1 means here high voltage, so it comes into, this is cutoff mode, and here saturation mode. So here the transistor is actually acting as a switch. So, when this is high, then this is low, and when it is low, it is high. In this way, this NOT gate operates, it is just a transistor. So, these are the basic building blocks, basic logic gates. Next, in next session, we will learn about the universal gates, that is NAND gate and NOR gate, which are called universal gates.